Chapter 10, Section 2, Basic Concepts of Regression Model and its Training. This section focuses on multiple regression analysis and related core concepts such as generalizability and overfitting, and model training. Linear regression is the most popular algorithm for supervised learning. Usually, in predictive analytics, we use many independent variables as input to the model. So, the linear regression model is usually a multiple regression model. Remember that a multiple linear regression model can be expressed by this form of equation. Before building a regression model, we should implement exploratory data analysis to understand our data. Exploratory data analysis, EDA for short, is an iterative process, and we can even say that it is a never-ending process. So, here, let me mention some essential parts of EDA for multiple linear regression analysis. First, we can implement univariate analysis to see the data distribution of our predictor variables and the outcome variable. As univariate analysis, we can compute descriptive statistics for each variable. And we can use popular visualization methods for univariate analysis. For categorical variables, we can use count plots. For numerical variables, we can use histograms and box plots. Since the outcome variable of a regression model should be numerical, we should use a histogram or box plot to visualize the distribution of the outcome variable. We should know that the outcome variable of a regression model does not need to be normally distributed. However, we need to check whether the outcome variable contains outliers that can significantly distort the relationship between predictors and the outcome. Remember that we use a linear regression model, assuming that the relationship between predictor and the outcome can be approximated by a straight line. That is, the predictor and the outcome are linearly related. However, some of the predictors can have a non-linear relationship with the outcome variable. Therefore, as a part of EDA, it is useful to create a scatter plot of the outcome and each predictor to visualize the relationship between predictors and outcome. You may find that some predictors are linearly related to the outcome, but others are non-linearly related or not related. You can also create bar plots to see the categorical predictors and the outcome variable. We can use a heat map to visualize correlation between variables. Using a heat map, we can find which predictors may have large impact on the outcome variable. Besides, we can check whether there are highly correlated pairs of predictor variable. If we find a pair of highly correlated predictors, we need to delete one of them. It is because a problem called multiple linearity will occur. Multiple linearity is a problem where a great amount of variance of an independent variable can be linearly predicted by other independent variables. If multiple linearity exists, the regression coefficients of each independent variable are not reliable. We can use the variance inflation factor to detect multiple linearity. Variance inflation factor is called VIF for short. Variance inflation factor can be computed for each independent variable. Variance inflation factor represents the extent to which the variance of an independent variable can be explained by other independent variables. If variance inflation factor of an independent variable is larger or equal to 5, multiple linearity exists. and the independent variable should be deleted from the regression model. In diagnostic analytics, multicollinearity is a serious problem, so we have to address this problem in regression analysis. However, in predictive analytics, we can ignore this problem if our purpose is just an accurate prediction, and the impacts of each independent variable are not our interest. In supervised learning, the prediction model should have high generalizability. Generalizability refers to a model's ability to adapt to new, previously unseen data. So, a model with high generalizability achieves high performance not only for existing data, but also for newly unseen data. The purpose of predictive analytics is to build a model that can predict new data accurately. Therefore, predictive models should have high generalizability. So, even if the model makes perfect or almost perfect prediction for existing data, it is useless if it performs poorly for new data. On the other hand, even if the model's performance is slightly lower for existing data, it is useful if it achieves moderate or high performance for new data. Overfitting is a phenomenon where a prediction model makes accurate prediction for a particular dataset, but poorly works for additional data. In other words, overfitting refers to a modeling error where a prediction model fits too closely to a particular dataset, and thus poorly fit other unknown datasets. Overfitted model only memorizes a particular dataset, but it does not learn underlying patterns in the data. So, overfitted model is not generalizable. There are various methods to prevent overfitting, but the most basic one is to collect more data for model training. It is because, generally, the more samples the dataset contains, the more representative the dataset is. To evaluate the model's generalizability and check the degree of overfitting, we can use the holdout method to train a prediction model. Model training is a machine learning jargon that means developing a model using data so that the model can achieve high performance. In model training using holdout method, we split existing data into training data and test data. The training data is existing data, and the test data is hypothetical new data. Usually, around 70 to 80% of the whole data is used for training, and the remaining 20 to 30% is used for test data. Next, we train the model using the training data so that the model learns underlying pattern from the data. After the model training, we evaluate the model's prediction performance. That is, we quantify how accurately the model predicts the outcome for the training dataset. Next, we apply the trained model to the test dataset and evaluate the model's prediction performance. We need to compare the model performance between prediction for training data and that for test data. If the model achieves high prediction performance both in training and test datasets, we can say the model has high generalizability and our model training is successfully completed. But if the model performance is much lower for the test set, the model's generalizability is low. That is, when a model performs much worse for test data than for training data, the model overfits the training data. When we completed the data preparation, we are ready to train our model. For model training, we input the training data into our model, here the multiple linear regression model. Using the training data, the model learned the patterns of relationship between the predictors and the outcome. When we input the training data into the model learns the optimal parameters of the model. A parameter is a value that characterizes the model equation. In a multiple linear regression model, parameters are the intercept and each partial regression coefficient. So, in this case, the model learned to find the optimal values for beta 0, beta 1, beta 2, and beta 3. From the training data, the model learns parameters and the optimal regression equation like this. It is often called the trained model. Using the trained model, we can make prediction for the outcomes for the training data. If the actual value and the predicted value are the almost same, that is, the predictions are highly accurate, the training was successfully implemented. If the observed value and the predicted values are widely different, the training didn't work well. So, we need to take measures to improve that model training, such as collecting more training data and adding predictor variables to our dataset. Then, the model computes the predicted value of the outcome variable for each case. We can evaluate the model's prediction performance by comparing the predicted value and the actual value. The test data is hypothetical new data, so a prediction model needs to achieve high prediction performance for the test data. After the model training and prediction, we need to evaluate the prediction performance of the regression model. When we use holdout method for model training, we can make prediction for both training and test datasets. Then, we can evaluate the model's prediction performance using the prediction results for training and test datasets. Here are the popular metrics to evaluate the prediction performance of a regression model. In the following sections, each of them will be explained in detail. Thank you for watching. Please thumbs up and subscribe to my channel.